Thank you, Anna, and thank all the organizers really for the kind invitation. It's a true pleasure being here, seeing friends, and all. And actually, I'm happy to be here also for a pure technical reason, because that made me actually force me to think also, to try to think also along practical lines, and you will see, which is not that typical to my usual talk. So it's really a pleasure, and again, I thank all the organizers and also Danny Palomar, who could not make it, for the kind invitation and the very special treatment I get here. Really thank you. So whatever we are going to do today is to try to give an information theoretic perspective on something which is kind of a big buzzword, if I may say, cloud radio. There are different terms for the very same thing. And to see whether we can identify what information theory has to say about, at least about some very focused ideas there, or even more about things that it's worth doing, meaning the benefits of the effort is worthwhile. And this talk is based on a joint work with Seok-Hwan Park and Osvaldo Simeone from NJIT and Onur Sahin from Interdigital. My work was partially supported also by the European network, Newcom Plus. So we'll start with the introduction to see where do we stand, discuss about the uplink, where I would like to focus on the multi-hop regime, which usually is not treated within simple information theoretic frameworks or considerations, move to the downlink, and this is the part I was addressing, trying to see for the parameters of LTE or 3GPP, what does this have to say? Not for what we or I especially would like to model, very simple Wiener-based models. But let's see here. This is actually a big deviation of my usual presentations. And conclude. So start the cloud radio idea. The cloud radio idea is different terms. I won't bother you with that. It actually says, look, all the base stations that we have, let's migrate the processing actually to a central unit sitting somewhere in the cloud, and those base stations become simple radio units, dumb radio units, oblivious radio units, use the word you like. So and that is actually promoted, motivated, at least appears in many papers of here it's only part of industrial companies, including Huawei that I see I miss here. And the idea is to have all the real processing here in the central unit, which means encoding, decoding for everybody. Those are just simple radio units, as used to be the very old relays, do nothing, amplify and forward, something of this kind. Here we'll do more and we'll see what is the advantage of more. And all those radio units are connected to the central unit by front haul. Front hauls, sometimes the terminology is back hauls, the same thing. Meaning digital connections that provide such and such rates in bits per second per hertz, whatever you wish, And those connections could be optical, if this is a macro cell, wireless, internet, or whatever you wish. So the idea is to see what's going on with such a system, where also base stations are of different kinds. Macro base station, pico base station, micro base station, whatever you wish. So that's the main idea. So where we should first see what information theory has, what's different. Why should we have a special address on such a topic from an information theoretic perspective? From a practical perspective, it's clear. New setup, so you should think how to design it efficiently. The advantage is, the standard advantage for that at least, is local employment of base station, deployment of base station, and what's more important from my point of view is the ability to control interference, which doesn't exist, for example, or to a minimal level today. Today, the cell site has to do all the processing, the base station. The users assigned to the base station have to be decoded. Others, sometimes it could decode them, remove the interference, sometimes no, take them the interference. The interference, though created by the very same system, it's not other wireless system, that could also be a problem. The system is basically interference limited, which once we didn't care, we didn't demand such high rates of communication. Now we do very much. So this is a way, because everything is processed in one unit, a way to cope with that efficiently. And so whatever is left is how really do we have the radio unit, receives signals through its antennas or multiple antennas. And that has to be somehow conveyed to the central unit. So what's the big deal? Through the front hood. So one could say, what's the big deal? A to D, and that's it. The problem is not that simple. A to D. Let's look at just simple, simple standards of analog to digital, which is known common public radio interface. And let's put the parameters of simple LT setting with 3 sectors and so on. The main thing is that whatever we have to convey is about 14 gigabits, which is not a trivial thing even with an optical link. So you better do something. The approach cannot be just forget, put a to this and that's it. So what is the state of art once this has been understood, and it has been understood? The standard approaches are what is known point-to-point front-hole compression. Okay, I have an analog signal, have somehow to compress it. If I know a distortion theory, it's even better. Though the distortion is not measured by, classical distortion, MMSE, or Hamming distance, or whatever you wish, because it's the rate, the coding rate that matters, not kind of distortion of the signal. It's related, but that we should keep in mind. And for that, even today, there are some proprietary algorithms, Alcatel-Lucent. Analysis of that is also not that trivial. We'll see why. And has been reported not that long ago. Simeone et al., Hongan Giuseppe here, sitting here, Park et al., and there are also even testbed results. By the way, all the references are shortly mentioned here at the end, and the slides are with you. They're all mentioned, so whoever is interested can find that there. The main idea that I'll focus is the multi-terminal front-hole compression, which is based really on quite modern theoretical information theory approaches. And it could be said, okay, of course, it's a nice thing, a nice research topic. even one can produce some nice result. What I want to convince you that there is more to that. And again, even that has been considered very recently, as you see, for the uplink and for the downlink, and we will really focus on that. Another very advanced approach is what is known structured coding. Meaning what? Okay, you move back, you step back from total obliviousness. You use codes that are structured, in this example, in this setting, lattice codes, linear codes, and you take advantage of this linearity to do things over this finite rate front holes. And uplink has been first considered by Nasser et al. I'm one of the co-authors, quite happy about that. Now considered to be old paper. And very recent important work on the uplink and the downlink appeared again by Giuseppe and his co-authors. Multi-hop front hole is, again, stepping back from idealized models and examining the system as is. Not always every cell site, every micro cell site that you have at home is connected directly to the central processor, even not through the internet. So sometimes there are some hops. One could be radio, the second optical. So it has an impact, and we'll see how. So let us start with the uplink. The model is as follows. Here we have the mobile station or end users or whatever they are, not necessarily mobile, connected to this radio units with a huge network assumed to be a matrix Gaussian channel, meaning Gaussian noise. Of course, all radio units, especially if they are dense, receive correlated signals. And those radio units are connected to the control unit, the cloud, by these front holes of different capacities. This is the basic model. And everything is multi-antenna, including the end users. The mobile users could be, not everybody uses just cell, could be a laptop or something even more complicated. This, whatever I said in words is written here, nothing different. A linear Gaussian vector model. And all front holes are normalized to the bandwidth of this channel uplink, so we don't have large numbers to deal with. And that's the natural normalization. So that means that for n symbol times on a front hole of capacity Ci, NCI bits could be transmitted reliably. That's the front hole. Reliably. How the front hole works, it's not our business here. Point-to-point compression, the simple thing. What is point-to-point compression? The most natural thing. Each radio unit receives whatever it receives through all its antennas, tries to represent this digitally via source coding approaches, transmitted on the front hole to the central unit, who decompresses it and gets something similar to the analog vector, multi-antenna, vector signal. Of course, not exactly because of the finite rate. And the decoder uses all of those signals together to decode whatever the messages of the mobile users, of the end users. That's the simple scheme. All the compressors work separately. The decoder, yes, decodes based on all signals together. So the analysis, which is rather standard, treating this analog signal as a Gaussian signal because of the obliviousness assumption. Obliviousness means the radio units have no idea What are the code books? What are the procedures used? Just no idea. And that's one of the principles, to make them dumb. So based on the on the backward test channel, we can represent a forward test channel, which means the signal, actually, the signal here is the original signal plus noise, well, the correlation of which we can design to optimize, and whatever we need, rate distortion, simple rate distortion. Don't forget, it's the distortion is to be defined later. Is the we can transfer, we can guarantee that the receiver, that the compressor gets this if the mutual information is smaller than the front hole, the ith front hole. And again, the correlation of this noise can be planned, designed, maybe optimized. So, something way more sophisticated is what is known distributed front hole compression, and that has been suggested first by Sanderovich, at the time my PhD student, and analyzed then, and that says the following. Look, indeed, the radio units do not cooperate, given. But those signals they receive, they are very correlated, at least in a dense environment. So, when we look at this signal, the receiver who decoded, decompressed this one, has a correlated information to that, to what is to be encoded. The receiver, the control unit, not the transmitter, still. So Wiener-Ziv source coding becomes natural here, of course, and you order the permutation, you order it as to optimize things. And that's the idea. This you compress the old way. The second one, already based on the side information that the receiver has, and so on. Every compressor on the line here has more and more side information from all past decoded signals, and the decoder decodes everything together. The message, the decoder is interested in the message. That's all. That's the Wiener-Ziv thing. And without bothering you too much with the details, what replaces the standard mutual information that we saw, simple point-to-point compression. We have this, of course, the conditioning should be appropriately interpreted. Remember, it's Wiener-Ziv. It's not the side information is not given both to the receiver or the transmission. Yet, this is what works, Gaussian assumption. And that is our measure, not distortion. Our measure is for example, the sum rate, which is the mutual information between the transmitted signals and all the reconstructed signals. That is our measure. Fine. The last thing to say is joint decompression and decoding. Why do we deal with decompressing and then having all the signals decoding them together? Why should we separate that? This is the cloud. This is the central unit. Let it do all together. It needs the messages. That's all. So it does everything jointly. And it can be shown that sometimes there are advantages to that, even over the Wiener-Ziv. And in fact, that has also appeared in the Sanderovich work. And if you look at this once again, this is exactly what years later has been called noisy network coding. As is. Appears there, without the terminology. Exactly, but exactly that. So the idea is, okay, it's easy to say how to do. How do you optimize all those things? So the idea to do that has been presented by Park et al. And, and again, here we try to maximize, indeed, to optimize over all the correlations of the the direct compression, decompression channels and the permutations, who first, who second. It's not the joint scheme. And quite amazingly, I'll add a few words later, this can be done, and the optimization is under the constraint that this is doable, the Wiener-Ziv rates. Otherwise, forget about that. It so happens that the optimization can be presented at the end, as in a simple as that we noticed by those guys, as a simple thing. Remember Gaussian assumption, so it's not that, it's rather immediate. As a condition on Karhunen-Loew, where Karhunen-Loew decorrelates all the things in a way, so all these are now uncorrelated, and everybody is, in the model is characterized by different channel gate and different noise. So it's not that bad. Can be really done, and conceptually quite simple. So that's the uplink with point-to-point compression, joint compression. Now let's look at structured coding. What is structured coding? No more Gaussian signal assumptions. We indeed do. All mobile units transmit code word structure from a lattice. Unfortunately, the channel is just a general additive channel, matrix additive channel. It does not provide integer coefficients. That's really a problem, a little problem. We'll see the cause. Yet, all radio units decode, because whatever they get, they linear, not integer, but linear combination of code words. Every radio unit tries to decode linear combination. Had it been integer on the right basis, it would be a code word. It tries to decode the code word. Then, over the front hole, no problem. Decoded the code word, so and so, there is such and such code book size, it can just transmit what code decoded. And that, once this one has enough linear equations, has enough from here, it can decode all the messages. That's the basic idea. Here written in words, using indeed this compute and forward strategy, and and as we said, we pay a price here. What is the price? It can be shown quite easily that the rate per mobile, simple scheme, this is the cut-set bound, cannot be larger than C in a symmetric system. All frontals are the same C. Cannot be larger than if you put a cut there. If you put a cut before there, it cannot be larger than the multiple axis channel where all radio units work together. Unfortunately, you pay a price. What is the price? The price exactly is the integer penalty price. And so this term appears here. I really don't want to go to don't have also the time to go to the details, but we know to characterize that. Listen bounds. What is the price you pay that the channel does not play for you? Channel is given. Does not see that the coefficient is integer. And that's the price. So it can be characterized. And let's see the results. As we said, we start with very simple models. This is the the Wiener model, actually. The circular three users, 3 radio units. Everybody is equipped with single antenna, circular model. Every radio unit is connected with the front hole, symmetric. Everything is symmetric with capacity C. Every mobile is received by its own cell with power, with the amplitude 1. The other cells with amplitude alpha, a bit farther away. And let's see what all those strategies give for this I even don't want to use the word simple, this naive scheme. What are we comparing? Again, the single cell processing which we have today. No cooperation, every cell decodes whatever its own user, and that's it. And conveys its own information, the information of its own user over the front hole that connects to whatever the information has to go to. Point-to-point front hole compression that we discussed, the most simple thing. The distributed stuff, the Wiener-Zipf coding scheme, the structure thing, compute and forward, and the cut-set upper bound. Here we have them. As a function of the mobile station SNR. And that's per cell summary divided by the number of mobile users or cell 7. So the single cell processing, of course, as we said, interference limited, this curve. This is what I want to focus on are the black curve and the red curve. The point-to-point compression and the distributed compression that has really quite an interesting advantage. I would say it's surprising. Usually the source coding, you don't expect too much surprises from sophisticated stuff. As you know, even simple examples, A to D conversion just by sampling, or optimal source coding of the source itself, just point to point, even with the MMSC. Okay, gives an advantage, of course. But here it's not that trivial, not only that. Also asymptotic advantage, With the SNR, the red curve does approach the cut-set bound. This is the cut-set bound. There's C, and that's the capacity of the multi-apple access channel where all radio units did cooperate. And what's interesting is it did this compute and forward, which starts not that good, but beats everybody else rather after, and that's exactly because of that. Because it starts not that good because at low SNR, its performance, the radio unit tend to decode trivial combinations. Too bad. When the SNR increases, it indeed beats everybody else, but not that much the distributed compression, which is an oblivious technique, knows nothing, no structure code, nothing about the transmitter, treats them as Gaussian signals. And so this is quite encouraging, I would say. Okay, this single hop. What about multi-hop? What do I mean multi-hop? Look, here we have, again, a more realistic model of the system, of the cloud system. Here we have the macro base stations, micro base stations that actually are not connected at all to the central unit, but through somebody else, through the macro base stations. For example, radio unit 6, this one, is not connected here directly at all, but it's connected through here and say through here and gets this, which is connected through this. So it's much more realistic. What can we say about that without being really too complicated, and then we lose the intuition and vision? First, the natural way to treat this is the directed acyclic graph. Here, just to give an example, here we have different radio units. All receive their own signals through antennas and are connected with this capacity front holes between them and between the central unit. Just the appropriate cyclic graph, very easy to this, is the appropriate acyclic graph is presented here. I save you the details how to analyze these things, but we'll focus on two things. One of the simple processing is just routing. Meaning what? You get digital information from the links from the front list that get to you, to the radio unit. You have your own antennas, the radio unit. Compress your own antennas, now you have the digital information also here. All is this digital information. Try somehow to route it through the links, through the outgoing front haul links you have with the appropriate rate. Not always you can do that. If your outgoing links are poor, then, you know. But that's a simple approach. And also appears not that simple to optimize, by the way, simple to describe. The optimization actually, and that we did, is based on the majority, because it can be represented difference of convex problems, but via the majorization minimization algorithm, which gives you at least, you know, stable point, nothing global optimum. That we cannot guarantee. So even that, the optimization is quite demanding. The in-network processing is a bit more sophisticated. It does what? First, decompresses the incoming signal, which is kind of stupid thing to do. They're already digital. Your front haul, outgoing front haul is digital. What's this decompression? And paying more. The idea is you have your own antennas. So and those signals are correlated to that at least in dense networks. Maybe decompressing then and then processing all together, even in a linear fashion, could be advantageous. Then you process and compress the old way, and transmit over your outgoing front hauls. Maybe that is not that bad an idea. We'll see. Of course, the damage is already there. You decompress, and compress, you pay with the additional compression noise. But the question is when, if at all, this could be advantageous. So both optimization of both strategies has been reported very recently, as you see in ISIT, yes, that we had on July. Let's examine a scheme. 3 hops. Here are the radio units, not connected directly to the central units, but via another set of radio units. This radio unit is connected to all radio units, n of them. This and this radio unit is just connected to half of the number of radio units. Just a model, n over half, n over half. That's the connection, and those all this set of radio units, that is the final hop, are connected to the central unit where they are front hauls with the appropriate capacities. And we again assume a Rayleigh model, IID, Rayleigh, the old model. That's Gaussian fading coefficients. One thing I didn't mention, and I'll mention, whatever I discuss here, CSI, chance state information, is known to all. Then we'll speak after. So the results we have here for this simple scheme, the routing thing, the black thing, and the in-network processing, the red thing, when the different front haul capacities appear just of the different kinds. And this, the x-axis, is just the number of radio units, n. The larger the number of radio units is, the more correlated the signals are, the more advantage that you can get from this in-network processing, because the signals are correlated. And you see it. And you see it exactly here. Now let us move to the downlink, which is usually a little more complicated scenario. What's the downlink? Again, central unit that knows everything, including CSI, which is a problem by itself. All messages to transmitted to transmit to all mobile units. The central unit is connected to this radio units via front halls or back halls, whatever you wish, with given capacities. All radio units are multi-antenna, transmit to the mobile stations, end stations. All are also multiple antenna, if you wish. A general big vector channel of multiple antennas, and that's the system. Whatever I said just appears here. Nothing more. Where the X's now stand for the signals that are transmitted by all radio units. And of course, the radio units, everybody is constrained, is limited by its own power constraint demands, according to the number of antennas, power amplifier, and whatever. The simple scheme, point-to-point compression. Point-to-point compression says what? Okay, this is the central processor. Knows all messages, encodes them in channel coding, tries to pre-code the optimal way it can. Pre-coding could be used. You remember, it's much easier to see what would have happened had all links been infinite capacity. Had all links been infinite capacity, it's very easy. Why? What do we have here? A MIMO, a huge MIMO broadcast channel. The central processor controls all antennas because it can convey whatever it wishes to everybody, infinite capacity. So it's a huge MIMO broadcast channel. A huge MIMO broadcast channel, there are quite nice pre-processing techniques. The optimal one that achieves the broadcast channel capacity is based on dirty paper coding, as we well know. Also, quite an old work with this friend of mine, Giuseppe. And other techniques, linear precoding, zero forcing, MMC optimal, many of them. So the precoding could be something of this kind, either linear or not linear. But here, C's are not infinite, unfortunately. We have somehow to compress. And here, this signal should have been transmitted by that. I cannot convey it as is, it's analog. So I compress it and try to convey it in the best way I can, that's all. That's the very simple idea of point-to-point compression. And the example, how it works, again, Wiener model, even simpler one. Each cell station is connected to two cellulars, its own assigned cellular with power 1, the other one, the interfering one, with amplitude alpha. And this is the central processor. Again, we have the direct test channel, which also assumes that the signals are Gaussian. In a way, we will see also the structure code, which boils to what? From here we see, to another MIMO broadcast channel with more noise. Remember, dirty paper coding has to know the signal-to-noise ratio. Okay, but it can be calculated. So you know. So the result is exactly, as the ideal result. But instead of having P here, you have P tilde. And P is related to P tilde by this simple formula, which has the capacity here. Let's put the capacity infinite. The capacity infinite, that removes P tilde equals to P. Let's put the capacity 0. The capacity 0. This becomes 0. This becomes infinite. P tilde is 0. No communication. Simple as that. The elegant formula just is maintained, just as a scenario. That's all. Quite elegant analysis. Now, let's move to multivariate compression. As we see, quite recent work. 1 minute. What multivariate compression? Who needs it? After all, the radio units do not cooperate. They just do not cooperate. They're separate. So what's this business of multivariate compression? How can you gain anything from this kind of approach? Let's see. To see, let's model a very simple system. A very simple system here, 2 radio units, 1 mobile station, that's all. Very simple. Here, as you see, compression, the direct channel, and the question, should we correlate the noises to make the signals somehow correlated or not? Okay, calculate what this gets received here. Simple model. Here is the calculation. This is the equivalent noise. This is correlation of the equivalent. Yes, you can minimize that by having those and those signals correlated. So it might help. Because what? Because the mobile station doesn't receive just the radio unit separately. It does receive a combination of the radio units. So let's go back. And what's the theory? How do we know what rates are? Usually before we just rely, simple source coding, mutual information, Wiener sieve, very simple. Here, what do we do? So it is based actually on a lemma that appears in El Gamal Kim's information theory book, why it's recent. It says what? As you see, the theoretical stuff is recent, not the application. Even the theoretical stuff is new. It says in other words, I want to construct such a scheme. There is a signal, could be a vector, of course, that should be compressed separately to n points, and those points, I want the signal, those signals, the reconstructed signals to be correlated, not Gaussian sum, to satisfy a joint probability law. Why? So do I wish. What is demanded to do that? This is demanded. This is the rate equation, overall subset, and so on, without going through. But that gives the theoretical basis to analyze what we want. We will see. It actually, having noticed something else, it gives more. Whatever we need, we will be needing is this vertex points, and we'll see. Though the general scheme kind of complicated, this special structure will help us a lot. Okay. So what did we say? We have Gaussian test channels for all, compressor, decompressor with noises to be correlated. The signal here, let us examine linear precoding, not optimal, we know. Represented by matrix A, and we optimize both together, the linear precoding matrix and the correlation coefficients of everything together. That's what we'll examine. Not a simple thing to do in practice. The idea, but now is clearer. Okay, so we maximize here a weighted sum rate, not just a sum rate. We can weight it the way we wish, under the constraints of what? Those are the constraints from the lemma from the book are very simple because it's Gaussian settings, so all expressions here are difference of log determinants, no big deal. All the mutual information is there. And this is the power constraint, that all radio units are constrained by their power. So this is the optimization. Again, this is not a convex, but could be put in terms of difference of convex problems. So majorization, maximization works. And now remember this thing that I showed. It so happens that you can do much simpler. It so happens that these vertex points you can achieve by doing again, arranging the users in the set in an order to be optimized, and encode each based on side information of the former one. Just in such, that's much simpler because it's point to point. The side information is easily accounted for, as we saw in the Wiener sieve. And the idea is that the vertex points are the same that the optimal. And that's by noticing that the former thing is a is a contra-polymatroid. So now we are in business because the optimization is quite straightforward. It's about noticing this mathematical fact. As you see, things are quite theoretically complicated for that. Not that trivial, at least for me. So, we said that's point-to-point compression, multivariate compression. How about structured coding also here? Structured coding, reverse compute and forward, thanks to Giuseppe here at this co-author, which says what? Trying again to model the dual of what we had in the uplink. The encoders do integer pre-coding, we see. That code words are transmitted to the base station, finite capacity links, no problem. Digital bits are transmitted. The base station can just transmit those code words and maybe play with amplitudes and so on to optimize things. So, let us indeed. The downlink, it's a very nice counterpart of the computer of the uplink computer forward, as we said. And let's examine the simple model, symmetric. All front holds are C. All base stations have the same power. Again, same number of mobiles as the base station, just to present results. A very simple thing. And as we said, this is the scheme that we described. The pre-coding is pre-coding over finite field, remember. The pre-coding over finite field. The same lattice code is used by each base station, so linear combinations, integer linear combinations of code words are code words. And so this is structured coding, not oblivious, not just oblivious. And all mobiles receive what they receive, try to decode their messages, which is a lattice code. Well, whatever one gets, one gets. And what's amazing, whatever one gets is again very similar to what we saw on the uplink. The minimum between the standard cut set and an expression which pays for which pays a price for the integer penalty. So on the downlink, we want to see also a comparison. Again, this very simple, naive, cyclic Wiener model that we saw, but now the downlink. What do we compare? Closed law. Single cell processing. With all the interference, you pay for the interference limited. That's the current schemes, without cooperation. This is the integer, meaning the structure code. Very nice, as you see. Really goes almost on the cut set bound, and then straightens out. And this, as you see, this is the integer price, a big price here. The black is point-to-point compression with linear processing, point-to-point compression with dirty paper processing, multivariate compression with linear, multivariate with dirty paper. As we see, multivariate with linear sometimes even builds the point-to-point with dirty paper. And multivariate really, again, we see quite nice approaches here the cut set bound. So as we said, the straightening of the line here of the structured code it flattens because of the of the integer approximation penalty. And again, quite nice and advantages we see. At least for of course, if the front hole is very large, forget about just do the optimal don't bother too much. The signal that you transmit will be almost as you want it to. So that's very nice. Now let's go. That's very nice. Binary model. What can be better? You know, such a naive scheme. How about 3GPP? Now things a little bit simple. And we look at the macro cell system, where in each macro cell there are n picocell base stations, say k mobile users, and macro cell base stations. And in this example, it's 2 users and 1 picocell station. Let's look at this thing, just 1 cell. Macro cells, 2 picocells. Sorry. Picocells, the front links, the front hole links are not the same for picocells that are connected from your home with something, who knows what, to the central unit, and the macro cell that has at least should have a good optical link or whatever. So that we cannot put the same. It's not a Wiener model. And the control unit. That's very nice. Here, it's not that I'm going to bother you. The parameters, as I said, this is not my style. But this is the system. This is the system with the parameters that you should examine. Not present as we have seen the naive models, and you see the gain, and you are happy with it. And sometimes, as you saw, even in very nice analytical formulas. Analytical, not just optimization. The idea is, okay, you just take what's there, and also the models of what they say rate. It's not some rate that they want, and they say, okay, some rate, forget about everything. No. There are really all those parameters. Forgive me on this, that I cannot really go through. But even whatever you want to see is a fairness metric that has to do with, with historical data rate that is normalized. And historical data rate also decays by the parameter beta that is defined. And there is also a fairness constraint alpha. Whatever they want, truly, just the thing that they have in their committees. And also, how do you measure performance? As we see, fairness measure, and there are also power power control constraints. So, uplink and downlink. Let's see more or less what can be said against the data rate, 100 megabits from the radius 100 megabits per second. We'll see normalized to the bandwidth, and the data rate is normalized. So we have 10 bits per second per hertz of the front hole. And here an example: 5 users, macro and pico. Macro is 3 times as much capacity than the picocell, and the different curves: black, point-to-point compression, red, multivariate compression, uplink. The parameter here is the number of picocells. More picocells, signals are more correlated. In the same area, you have more cell sites. So you see, the more picocell, the advantage between the point-to-point and the multivariate compression is greater, as expected. Again, now the performance they want, for example, the 5 percentile, not some rate, that's what they want. Whether good or not, don't ask me, that I don't know. The 5 percentile rates that what do they want? What's interesting is, again, the advantage of the multivariate compression, which we see is significant. Truly significant. Quite a surprising thing. One thing is significant over this Wiener model. Another thing is significant under those performance measure. And here we had the performance measure, the cumulative density function that we want to see. What is the probability that the rate is more than that and that? And that's the uplink. Downlink, again, more or less same figure, twice, rate-wise, twice the advantage. More or less same figures. The parameters are really less important. So, and that's their parameters. So let us conclude and be more or less on time. Whatever I try to provide is indeed a kind of a survey of front hall designs using really what I think is advanced theoretical thinking. Even though those not using this theoretical result or the other theoretical result. And we've seen that multivariate compression, we compare multivariate compression, point-to-point compression, also up-downing and structured coding, and multivariate compression is advantageous over to-point compression, especially when the demands of the data rate, reliable data rate, is high. The system is dense, as is current demands, and the SNR is large. Otherwise, you cannot supply the high data rate anyway, even if you're a single user alone. Structured coding, though it's not that I recommend using that in practice because of the obliviousness, structured coding outperforms all other schemes in the regime of high SNR when indeed the front hall capacity becomes the main bottleneck. Routing in network processing as compared to in-network processing, again, loses the game when the scheme is dense, and then we have really correlated signals, then in-network processing is advantageous. And as we've seen in the end, the 3GPP scenario, when we examine sum rate, cumulative density function, proportional fairness, utility, cell age, the 5% cell age throughput, quite an advantage. So almost twice, at least the minimum 60% of advantage in terms of rates. So things that we haven't discussed. CSI, chance state information. Very important. Everybody knows everything. That's not the case. Especially not uniformly. The central unit knows maybe less than what the radio units know that they receive the signal. They can estimate that. Actually, analysis in some of the reference is available, and sometimes it's very simple. You can do the very same, actually, considering under certain models of imperfect chance state information, still get most very good results by the same techniques. Remember, we assume everything is Gaussian, this oblivious processing. That's why this can be done. Other thing is unreliable front links. Here, the front links are given. These are the capacity everybody knows. Very nice. Of course, if this is pre-assigned to you, if you build it, you have an optical, that's fine. But if you work on the internet, sometimes it's this, sometimes that, sometimes nothing. Who knows? And not always this information can be conveyed backwards to everybody. So we have considered this as another chance state parameter, not necessarily the failing, not necessarily the age measures, but it's unknown. Maybe the statistics is known, but it's unknown. How do we cope with that? Do we take the Shannon approach of compound chance that we design for the worst case? Not at all. Why should we? So that falls exactly within what is known variable to fixed channel coding, or in a simpler way, the broadcast approach. Forget the broadcast channel, point to point. Meaning that I want to achieve what you have with analog television. Analog television, there is one transmitter. You have a good channel, you have a good picture. You have a bad channel, you have a bad picture. With digital television, you have a good channel, you have the picture. You have a bad channel, you have nothing because you decode. You have an excellent channel, the same picture as she has. How do we go back to the analog performance? We can. And the information theoretic basis of that is variable to fixed channel coding, not source coding. Appears here. Can be incorporated into that. Again, we saw structure code and their advantage. Oblivious codes, we worth examining, taking a step backward, examining maybe with something which combines both in a natural way, not switch here and switch there. That's not a good idea. Even here, the cloud, even with the multi-hop, the cloud structure was quite simple. No, it's not always reality. Single control unit is very nice for representation. Also not exactly the reality. As we said about structure coding, we saw this the expression for the uplink and downlink quite similar with the integer penalty. Actually, it's much more into that, and there is something like uplink, downlink duality as it in the broadcast channel, the multiple access channel. Also under this, the recent work has been presented just now in ISIT. Bobak and company. Again, linear versus non-linear precoding. We don't like to do so much non-linear precoding in practice, and no, that's quite understandable, even those who really like this dirty paper stuff like your humble servant, but still, practice one should be careful. And there are quite a number of other things to consider. With that, I'll stop, and thank you all.
Thank you very much for your perfect talk.
Thank you, Hannah. Thank you. What can I say?
So the CRAN model is introducing this really cheap base thing rather than macro base stations, very cheap nodes. But then what I see from when you do the information theoretic analysis, you need these nodes to apply really complicated coding, decoding, multi-terminal compression, and also you need all these channel state informations. So does it really make them kind of dumb?
No, the idea is that this kind of things, quite standard, if you think about what it needs, multivariate compression and simple compression, whatever the site does, the radio unit does, is more or less the same. Is the decoder much more complicated? It doesn't know even the site information. So it takes, has a code book and transmits, and more or less it's standard technology as is even now. Because in a way, even now they say, okay, we cannot, that was, I started with that, with the first presentation, we cannot just do A to D and forget about it. Just cannot, even now. So even now they do source coding. So the question is, is it cost-wise to use, sophisticated source coding versus dumb source coding? Source coding you must do. That's not a question anymore. That was the.
They talk about this radio over fiber, right?
What?
Radio over fiber.
Yeah, even that. I even said, okay, fiber, go fiber. And the demand of 50, You know what is that?
14
Yeah, 40. That was the very first slide. So that's really surprising. And over this very standard scheme. That's why I made all of them, all of the companies, I mean. Truly all. I think in the reference list here, here, 14 gigabits is not trivial at all, even no optics. That's why when all companies, and let's go to the references indeed. As I promised, all references appear here. Those are not it's not really a minimal reference list, that only those that I specifically mentioned. There are many more, of course. So you see, things like Alcatel-Nosa, China Mobile, Ericsson, Huawei, all.
So what about the delay that you introduced by using this vector quantitation?
So the delay is really not significant, because what is vector quantization? Of course, theory, you need infinite length symbols. If you ask what is really the processing length, is way below the coding length that we use now. If the coding is sophisticated, it's kind of turbo, LDPC or whatever. Way below, to provide almost negligible degradation as compared to those. Way below. So it's really something to think about, seriously.
Hi, I'm Fernando Tavares from Aalborg University. And one question that I would make that, let's say, a network operator would make is, one of the biggest advantages of having such a Cloud RAN thing is to have this interference management feature, joint processing at the central unit. However, as you said, we start to have a front haul limited network. If we try to balance this, how much do we lose by having the limitation on the front haul, and how much do we gain by being able to joint process everything there? In the sense of interference, actually, what would be better?
A very good question. Actually, the answer was many times on the curves, and forgive me that I didn't indeed emphasize that. Truly. That, for example, you see, this upper bound cuts it bound. This says joint processing over. This part of the curve, the black, this thing, says, look, infinite backhaul, free. This is the part. This is the part says zero channel noise, free. So you are limited only by the backhaul. That shows exactly. Exactly. And what we see, we are not far from there. Meaning what? In different points. Meaning what? No point to consider more sophisticated stuff. No point to rely on the fact you say, okay, and if there are new the codebook structure. After all, those are not gas signals, those are codebook. Whatever. Optimize over them. Not only just rely on lattice technology. Optimize over everything that we don't know how to do, of course, theoretically. Say you knew. No big deal. You cannot beat this by no means. Not now, not ever. Of course, under the same parameters. And when we had it, such a curve in every simple example I have given. Happening as well. Oh. You see, you say, okay, if I work here, yes, maybe there is something else to go. No, nobody said that this is achievable. It's not. But if we work here with enough, power, and we must work now with high signal-to-noise ratio, because otherwise forget about the high data rate.
But perhaps the question was, is it worthwhile to even do that? And I think that it is, because when you see the peak curve, that is the regular single-cell processing, you see that the gain is pretty
No,
high.
the single cell processing, everybody already agrees that that cannot work. That is agreeable all over now. That's agreeable by all companies, I mean not theoreticians. That this cannot continue anymore. That's agreeable. And we see why. It flattens in everything. It flattens.
And if I may, I still have one question. Now, when we start thinking about microcells, picocells, and even going even smaller and smaller with very dense networks, there's a clear need for going for TDD mode, right? Because of the imbalances in uplink, downlink ratios, and so network operators want that. Are you considering any type of framework for analyzing also this type of situation in which some of the radio units are transmitting while others are receiving? Does it change anything?
Yeah, of course. Once there is simultaneous transmission and receiver, it changed the picture, but could be accounted for in a way. And actually more than accounted for. It brings another topic up. For example, duplex processing. Duplex processing. Same cell transmits and receives, even same cell. It's not that trivial. And, it's not the simple answer, it's not really doable, not in practice. That was also my thinking. It's just not that far away until I saw reports also from Huawei that they are very serious about that. They have many dozens of people working on that, and I think even one of the missions of the new Paris, we'll see Merwan Debas, who will ask him, is that. So not only different cells, but the very same cell was transmitting and receiving, which is even worse. You cannot even imagine that. Still, probably doable. By the way, very same cell, once there was what is known F1 relay, F1, meaning that it has been used commercially, meaning, of course, it's easier to receive a frequency F1 and to retransmit analog on F2, and then, F1, F2 is standard and has been used for many decades. In the 60s, there were things that are called F1, F1. All analog, you understand, 60s. We are speaking about the 60s. Somehow they reached an isolation of 135 dB cross-couple loops. Not trivial, huh? F1, F1. You receive on F1, you transmit on F1. Okay, you know what you transmit. The receiving is delayed, and you remove, but removing your transmission with such an accuracy is not trivial. So maybe it's doable truly. Who knows? I don't know. But the fact that all those companies are interested in that make this a realm. Of course, that should be introduced in the analysis, what I say, not in a trivial way. Meaning not that you have another interference from here, another interference from there. But in a more sophisticated way, for example, we know that sometimes duplex achieve full DOF, degrees of freedom, like they were separated, like you had two different frequencies for free if you have enough users. One of the papers appears in ITW that we had in EPFL 2 years ago. So and the techniques are not trivial. Interference alignment at its best. Oh, well,
Thanks.
thank you. Thank you so much. Thank you so much. Thank you. Thank you all. Thank you, Anna, and thank all the organizers really for the kind invitation. It's a true pleasure being here, seeing friends, and all. And actually, I'm happy to be here also for a pure technical reason, because that made me actually force me to think also, to try to think also along practical lines, and you will see, which is not that typical to my usual talk. So it's really a pleasure, and again, I thank all the organizers and also Danny Palomar, who could not make it, for the kind invitation and the very special treatment I get here. Really thank you. So whatever we are going to do today is to try to give an information theoretic perspective on something which is kind of a big buzzword, if I may say, cloud radio. There are different terms for the very same thing. And to see whether we can identify what information theory has to say about, at least about some very focused ideas there, or even more about things that it's worth doing, meaning the benefits of the effort is worthwhile. And this talk is based on a joint work with Seok-Hwan Park and Osvaldo Simeone from NJIT and Onur Sahin from Interdigital. My work was partially supported also by the European network, Newcom Plus. So we'll start with the introduction to see where do we stand, discuss about the uplink, where I would like to focus on the multi-hop regime, which usually is not treated within simple information theoretic frameworks or considerations. Move to the downlink, and this is the part I was addressing. You take advantage of this linearity to do things over this finite rate front holes. And uplink has been first considered by Nasser et al. I'm one of the co-authors, quite happy about that. Now considered to be old paper. And very recent important work on the uplink and the downlink appears again by Giuseppe and his co-authors. Multi-hop front hole is, again, stepping back from idealized models and examining the system as is. Not always every cell site, every micro cell site that you have at home is connected directly to the central processor, even not through the internet. So sometimes there are some hops. One could be radio, the second optical. So it has an impact, and we'll see how. So let us start with the uplink. The model is as follows. Here we have the mobile station or end users or whatever they are, not necessarily mobile, connected to this radio units with a huge network assumed to be a matrix Gaussian channel, meaning Gaussian noise. Of course, all radio units, especially if they are dense, receive correlated signals. And those radio units are connected to the control unit, the cloud, by these front holes of different capacities. This is the basic model. And everything is multi-antenna, including the end users. The mobile users could be not everybody uses just cell, could be a laptop or something even more complicated. This, whatever I said in words is written here, nothing different. A linear Gaussian vector model. And all front holes are normalized to the bandwidth of this channel uplink, so we don't have large numbers to deal with. And that's the natural normalization. So that means trying to see for the parameters of LTE or 3GPP, what does this have to say? Not for what we or I especially would like to model, very simple Wiener-based models. But let's see here. This is actually a big deviation of my usual presentations. And conclude. So start the cloud radio idea. The cloud radio idea is different terms. I won't bother you with that. It actually says, look, all the base stations that we have, let's migrate the processing actually to a central unit sitting somewhere in the cloud, and those base stations become simple radio units, dumb radio units, oblivious radio units, use the word you like. So and that is actually promoted, motivated, at least appears in many papers of here it's only part of industrial companies, including Huawei that I see I miss here. And the idea is to have all the real processing here in the central unit, which means encoding, decoding for everybody. Those are just simple radio units, as used to be the very old relays, do nothing, amplify and forward, something of this kind. Here we'll do more, and we'll see what is the advantage of more. And all those radio units are connected to the central unit by front hole. Front holes, sometimes the terminology is back holes, the same thing. Meaning digital connections that provide such and such rates in bits per second per hertz, whatever you wish. And those connections could be optical, if this is a macro cell, wireless, internet, or whatever you wish. So the idea is to see what's going on with such a system, where also base stations are of different kinds. Macro base station, pico base station, micro base station, whatever you wish. So that's the main idea. So where we should first see what information theory has, what's different. Why should we have a special address on such a topic from an information theoretic perspective? From a practical perspective, it's clear. New setup, so you should think how to design it efficiently. The advantage is, the standard advantage for that at least, is local employment of base station, deployment of base station, and what's more important from my point of view is the ability to control interference, which doesn't exist, for example, or to a minimal level today. Today, the cell site has to do all the processing, the base station. The users assigned to the base station have to be decoded. Others, sometimes it could decode them, remove the interference, sometimes no, taking them the interference, though created by the very same system. It's not other wireless system that could also be a problem. The system is basically interference limited, which once we didn't care, we didn't demand such high rates of communication. Now we do very much. So this is a way, because everything is processed in one unit, a way to cope with that efficiently. And so whatever is left is how really do we have the radio unit, receives signals through its antennas or multiple antennas. And that has to be somehow conveyed to the central unit. So what's the big deal? Through the front hood. So one could say, what's the big deal? A to D, and that's it. The problem is not that simple. A to D. Let's look at just simple, simple standards of analog to digital, which is known common public radio interface. And let's put the parameters of simple LT LT setting with 3 sectors and so on. The main thing is that whatever we have to convey is about 14 gigabits, which is not a trivial thing even with an optical link. So you better do something. The approach cannot be just forget, put A to this and that's it. So what is the state of art once this has been understood, and it has been understood? The standard approaches are what is known point-to-point front-hole compression. Okay, I have an analog signal, have somehow to compress it. If I know a distortion theory, it's even better. Though the distortion is not measured by, classical distortion, MMSE, or Hamming distance, or whatever you wish, because it's the rate, the coding rate that matters, not kind of distortion of the signal. It's related, but that we should keep in mind. And for that, even today, there are some proprietary algorithms, Alcatel-Lucent. Analysis of that is also not that trivial. We'll see why. And has been reported not that long ago. Simeone et al., Hongan Giuseppe here, sitting here, Park et al., and there are also even testbed results. By the way, all the references are shortly mentioned here at the end, and the slides are with you. They're all mentioned, so whoever is interested can find that there. The main idea that I'll focus is the multi-terminal front-hole compression, which is based really on quite modern theoretical information theory approaches. And it could be said, okay, of course, it's a nice thing, a nice research topic. Even one can produce some nice result. What I want to convince you that there is more to that. And again, even that has been considered very recently, as you see, for the uplink and for the downlink, and we will really focus on that. Another very advanced approach is what is known structured coding. Meaning what? Okay, you move back, you step back from total obliviousness. You use codes that are structured, in this example, in this setting, lattice codes, linear codes, and you actually